Hello everyone, welcome to Tech-Lavya. Please like, share and subscribe.
Now we are solving May 2018 question paper, and in today's lecture we are going to see part 5 of that question paper, which is going to be the last in this series. Okay, and we had already solved till question number 5b. So let us see what is question number 5c, which was asked for 4 marks. Now it says that prove that if the phase impedances are same, the power drawn by the balanced delta connection. Okay, the power in delta connection is 3 times the power in star connection. Okay, so what we will be doing is we will be dividing the power into star connection and in delta connection. Okay, so first let us write the relationship of voltage and current in star and delta connection. Okay, so what is the relationship in star connection? Here the phase voltage is given by VL by root 3, and the current, the line current and phase current are same. Whereas in delta connection, line voltage and phase voltages are same, but phase current is given by line current by root 3. So you have to remember these relations. Now it is very easy for us to do calculations. Okay, now here let us calculate the current, which will be the voltage upon the impedance, isn't it? So what will be line current? This is same as line current, correct? So let us put the value. So it will be this. Okay, now let us calculate the power. Say PS represents the power in star connected load. So it will be root 3 times VL IL cos phi. We just have to put the values. Correct? Root 3 gets cancelled and we get PS is equal to VL square upon ZPH cos phi. Let this be equation number 1. Now we will calculate the power in delta connection. Okay? Yes. So now here the power will be root 3 times VL IL cos phi. Right? So I have VL. So what will be IL? Now let us calculate IL here. So IL will be root 3 times IPH, which will be root 3 times what will be IPH? It will be VPH upon ZPH, right? So let this be equation number 2. Put the value in equation number 2. So now my equation number 2 becomes P is equal to root 3 VL into root 3. VPH is nothing but VL, isn't it? So I will simply write VL ZPH into cos phi. Now here root 3 is not getting cancelled, right? And let this power be PD. D denotes delta power. Okay, so this comes out to be 3 VL square upon ZPH cos phi. This becomes equation number 3. Now you compare equation number 1 and equation number 3. Right? So by comparing equation number 1 and equation number 3, what can I say? That the delta connected power is 3 times that of the star connected power, isn't it? So we have proved this. So let us go to the next question. The next question says 3 identical coils having the reactance of 20 ohms, resistance of 10 ohms, okay, star connection for 440 volt 3-phase line. Okay, so we have to calculate the currents, power, etc. So first let us write down the given value. So given value is reactance is 20 ohms and resistance is 10 ohms. and the line voltage is given to be 200 volts and the connection is given as star connection. Fine. So in star connection we have just seen that phase voltage is equal to line upon root 3. So that becomes 400 by root 3. That comes out to be 230.94. Okay. Now let us calculate ZPH. What is ZPH? The combination of resistance and inductance. So it becomes R plus J20. So when I convert this into polar form, this becomes 22.36 with angle 63.43 degrees. Okay, and with this I get the magnitude of ZPH to be 22.36 and I get phi to be 63.43 degrees. So by using this phi value I can calculate cos phi, and cos phi comes out to be 0.447. Okay, now I have all the values, so I will calculate the phase current. Since it is star connection, it is same as the line current, which comes out to be VPH upon ZPH. So it is 230.94 upon 22.36, and this comes out to be 10.32 amperes. So this is one answer. Okay, then they say active power, reactive power and apparent power. So active power is represented by P and it is given by root 3 VL IL cos phi. So it becomes root 3. Okay, VL was 400, IL was 10.32 and cos phi was 0.44. Correct? So this P becomes 3199.95 watt. So this is another answer. Let us calculate the reactive power. Reactive power is same, but instead of cos phi we have sin phi. So we have to find the value of sin phi here. Okay, but since we have phi with us, we can calculate sin phi, isn't it? So when we put the value of these, when we put the value of VL, IL and sin phi, Q comes out to be 6399.96 watts. So this is another answer. Now the apparent power, which is represented by S, is given by root 3 VL IL. So it will be root 3 into 400 into 10.32. So that comes out to be 7155.37 watt. So this is S. Okay. Now if you read it, it says that we have to calculate the reading of each wattmeter also. Okay, so what we are going to do is, for this what we are going to do is, we have active power, isn't it? So this active power is given by W1 plus W2. Okay, and in 2 wattmeter method, tan phi is given by root 3 W1 minus W2 upon W1 plus W2. Okay, now we have phi with us, isn't it? So what we will write is, we will put the value of phi here, and we know the value of W1 plus W2, which was P, which came out to be 3199.95. So we will put this value 3199.95. Okay, so with this we get W1 minus W2 to be 3694.98. Now let this equation be equation number 1 and let this equation be equation number 2. So by using equation 1 and 2, we can calculate the value of W1 and W2. Because we have W1 plus W2, we have W1 minus W2. So by calculating this, we get W1 to be 3447.47 watt and W2 comes out to be 247.513 watt. So we get this answer as well. Okay, let us go to the next question now. The next question is question number 6B. It has been asked for 6 marks. It says a series resonance circuit has an impedance of 500 ohms at resonance frequency. Okay, the cutoff frequencies are given. Now remember, here cutoff frequencies are given, but the resonant frequency is not given. So we have to find out the resonant frequency, RLC and the Q factor. Okay. Now the bandwidth, what do you mean by bandwidth? It is the difference between higher cutoff frequency and lower cutoff frequency. So higher cutoff frequency is given by 10 kilohertz. So it is 10,000 hertz minus lower cutoff frequency is 100 hertz. So it means that bandwidth comes out to be 99000 hertz. Right? Now if you know, if we talk about the relationship between higher cutoff frequency, bandwidth and resonant frequency, then the relation is given by higher cutoff frequency is resonant frequency plus half of bandwidth. Similarly, the lower cutoff frequency is given by the resonant frequency minus bandwidth by 2. Okay, fine. So when we add these equations together, what do we get? The resonant frequency comes out to be this higher cutoff frequency plus lower cutoff frequency divided by 2. So it comes out to be 5050 hertz. This is nothing but my resonance frequency. So this is one of the answers. Okay, fine. Now the second point is the values. Now it is given that it has the impedance of 500 ohms, right? Okay, so it is given as 500 ohms. Now the bandwidth is given by R upon 2 pi L. If the bandwidth is given in hertz, if bandwidth is given in radians, then it is represented by R upon L. If it is given in radians per second, please remember this, okay? But here we have it in hertz, so we will be using this equation only. So can we calculate L by using this? Of course. So it becomes R upon 2 pi into bandwidth. Isn't it? So we shall be placing the value. When we place the value, we get the value of L. That comes out to be 8.038 millihenry. So we got the value of L. Okay. Now let us calculate the value of XL. So XL is 2 pi FL. So what is this? Resonance frequency. Okay. So we will put the value. So 2 pi multiplied by 5050 into 8.038 milli. So 10 raised to power minus 3. So XL comes out to be 255.05 ohms. But we know that at resonance XL is same as XC. It means XC is also 255.05 ohm, right? But what is XC? XC is 1 upon 2 pi FC, right? So what would be C? It would be 1 upon 2 pi F. What is this frequency? Resonance frequency. Isn't it? Multiplied by XC. Okay. So we can calculate the value of C by putting all the values, and it comes out to be 0.12 microfarads. So we have calculated the value of C also. Now let us talk about Q factor. So Q factor is given by 1 upon R square root L by C. So now we have all the values. So simply we can put the values here and we will be calculating it. So the value of Q factor comes out to be 0.517. Okay. Now the same can be done in one more way. Okay. Let me tell you that. Yes. So Q factor has got one more equation, and that is given by resonance frequency upon bandwidth. So resonance frequency is 5050 and bandwidth is 9900. So it also comes out to be 0.51 Q factor. So you can use any of these two formulas. Fine. Let us go to the next question. Now the last question, which was asked for 6 marks, says that we have to draw the phasor diagram for lagging power factor for single phase transformer. So again, this has been discussed in the 4th chapter, that was single phase transformer, and we have done the phasor diagram for resistive, that is when power factor, the phi value is 0, or lagging power factor, which is inductive load, and leading power factor also, which has capacitive load. So we have seen all three kinds of phasor diagram. You can refer to that lecture in transformer chapter. Okay. So with this we finish May 2018 question paper, and this comes to the end of today's lecture as well. Thank you so much.